Okay, thanks. So I'm going to talk about a method to model better two-way coupling between geomechanical modeling and flow simulation for stress-sensitive reservoir. So first, what is a stress-sensitive reservoir? A stress-sensitive reservoir is a reservoir whose porosity, Phi, or permeability, K, depends on the pore pressure, so P. A typical example of those kind of reservoir are soft compacting formation like chalk, weak sandstones, unconsolidated sandstones, or eventually highly overpressured formation which experience significant depletion. The current practice when we want to simulate compacting, so stress-sensitive reservoir, it is to couple a flow simulator like, for instance, Eclipse, T-Navigator, or whatever, and a geomechanical simulator, which like Visage or Abacus or Elfen. And those two simulators will basically connect between each others to equilibrate the pressure. The geomechanical simulator will evaluate, for instance, the change of rock deformation and therefore the change of porosity, and the flow simulator will evaluate the change of pore pressure and the change of flow. This is a very slow and time-consuming process. So on this slide, what you see is that so for the great majority of reservoir, there is no or little compaction, and therefore it can be neglected when we want to evaluate the impact of compaction on production. However, for those kind of stress-sensitive reservoir which compact heavily, the response of the reservoir and the production can be severely impacted by depletion or injection. So here on this slide, what you see is a case of a synthetic field which is derived from the North Sea chalk field. So in North Sea, there are a lot of chalk fields which are very soft compacting formation. And what you see here is that it's the typical production profile of a well. If we consider stress sensitivity, so compaction and its impact on the production, and if we do not take that into account. So if we compare, compaction cases are represented in continuous line. So the green one is the oil rate, the red one is the gas oil ratio, the black one is the bottom hole pressure. And if we don't consider compaction, then this is a dashed line. So for instance, the bottom hole pressure here, the gas oil ratio here, and the oil rate which decline. So what you see is that compaction is a very effective, impacts heavily the production, and it sustains in that case the production because there is what is called the compaction drive. In fact, the reduction of pore volume which is associated with compaction will help sustain the pore pressure and therefore will ensure a good deliverability of the well, even if there is a reduction of porosity and permeability. So clearly in this case, in the case of this kind of field, it is not possible to neglect compaction and to do a conventional flow simulation. It is necessary to take geomechanics into account. However, this is and that's what is written here in red, it is really a very time-consuming process. And if you want to evaluate one or two scenarios, it's clearly possible, it's manageable. Now, if you have to do a full uncertainty analysis or to evaluate numerous scenarios because you want to know the better optimization of your well, it's almost impossible unless you have a significant computational capacity and a lot of time, which is not always the case. So what I'm going to introduce from now is simply a method to mitigate this issue and to evaluate compaction faster. So, at the basis of this method, which I'm presenting, we should pay attention to what is the behavior of a typical cell in a flow and geomechanical simulation model when there is compaction. So here is a graph which shows the pore volume multiplier of a cell which is compacting versus the relative change of pore pressure. So here we are at 1. Okay, this is the initial condition, and the initial pore pressure is 0. I mean, the initial relative change of pore pressure is 0. Huh? The pore pressure is equal to the initial pore pressure. What happens is that when we start depleting, for instance, this cell, we will see that the pore volume will decrease. It's almost negligible. It's basically at this point, it will still be 0.999. It's almost the same volume as initially. And then all of a sudden, there is the pore collapse phenomena, and we can observe a severe reduction of pore volume multiplier. So this is the black curve that you see here. Okay. Now, let's consider two scenarios. The first one where we deplete up till a certain level and then we reinject. So what would happen is that is follow the green line. We are here initially at 1. We deplete down to 50 bars, I mean minus 50 bars of depletion. And then there is pore collapse. The pore volume reduced severely down to 0.9. And then we re-inject. So we repressurize the reservoir due to injection or because of a shut-in. Then you would see, the pressure rebound, and the pore volume will increase again. However, it will increase at a slope which is perfectly parallel to the elastic behavior here. Okay, so there is a loss which is irreversible of porosity. Now, if we deplete again, then we will go back to the black line and follow again the black line. If we consider a second scenario where we would deplete much more, this is the orange line, then again, even if we deplete, we re-inject and we recover part of the lost porosity, we won't recover it fully. And if we deplete again, we resume depletion, we will catch back the black line. So what matters, and that's the message I want to convey in this slide, in this graph, is that fundamentally, the stress path or the pore volume behavior of a cell which is compacting is always defined by this black line, the compaction line. And when there is a cycle of repressurization, it follows a slope which is parallel to the elastic one, okay, almost one. So that we should bear that in mind. Another observation is that not all the cells in a model will behave the same. Some will be weaker, so they will compact faster or earlier, or they will be at a stress regime which makes them more prone to compact. Here there are 3 cells. Okay, so the cell 1, which is in blue, so this cell experienced pore collapse after 20 bar of depletion, and then it compacts slowly down to 50% of reduction of pore volume. We can compare it to another slope, another cell, which is cell 3, for instance. The cell 3, which is in green, will compact only after 100 bar of depletion. However, once it starts compact, we can see that it will follow the same slope as the blue one, as the cell 1. So cell 3 and cell 1 have the same slope for compaction in plasticity. However, ultimately, they don't reach, the same extent of compaction. So cell 1 in blue will reach 50% of compaction, whereas cell 3 in green will reach only 20% of compaction. This is PVM compact. So that's what differentiates them, is not the slope, but the amount of compaction, so the PVM compact. If we consider another cell, cell 2 in red, this cell will fundamentally compact after experience pore collapse after, let's say, 70 bars of depletion. It will compact at a much faster path than cell 1 and 3. Okay, the slope is much steeper. However, ultimately, it reaches the same amount of compaction than cell 1. Okay, so which is 50%. So we could use those two metrics, the slope when there is compaction, when there is plasticity, and the extent of the compaction, to classify the cells and to classify the cell and to say, okay, this cell is very different in its behavior than this one. So the idea behind the fast flow geomechanical coupling that I propose is the following: is that first we perform a synthetic geomechanical run, which is a uniform increment of depletion. For instance, we do a first step, which will be initial pore pressure minus 20 bar. Second, which is initial pore pressure minus 40 bar. Everywhere in the reservoir. It's something which is impossible in reality, but, or let's say, which is not realistic in the case of a feeder model, but it enables us to get this black line. Okay, so it's just a trick to get the black line for every cell. Once we have this geomechanical run, which may be the most time-consuming part of this workflow, then we can derive for every cell the rock compaction table, which is in fact a table which gives the pore volume multiplier and the permeability multiplier versus the relative change of pore pressure. And then in step 3, we can classify all those cells in rock classes. We use the two metrics that we have shown, that we have seen before. So the slope of compaction, which is here, how heavy is and quick is the compaction once there is plasticity, once there is pore collapse, and the second matrix, which is the extent of the compaction, the PVM compacted, which is how much does my cell compact. So in that case, 20% or 50%. And I classify all those cells. I define classes, and for each classes, I find a medoid, which is a reference compaction table, so a reference cell. And in step 4, I repeat. I perform a flow simulation with the rock classes that I have defined. Okay, so maybe I have 10 rock classes and 10 rock compaction table, and I do my simulation, my flow simulation. I repeat the steps 3 and 4 with an increasing number of cells of rock classes. So 20 rock classes, 50 rock classes, 100 rock classes, etc., until we reach quite a large number, 500 or 1000. And what I would observe in step 6 is that at some point, the outcome of the flow simulation that I get is the same regardless of the number of cells that I have in my rock classes. So if I have 20 rock classes, or if I have, for instance, 100 or 200 rock classes or 500, it yields exactly the same results. Then that would mean that we have reached the convergence, and that basically our flow simulation replicates perfectly the fully coupled flow geomechanical simulation, which is the very time-consuming part of our job. So let's apply it. In that case, so still on this small chalk model of stress-sensitive and compacting reservoir, I have classified, I have performed one geomechanical simulation. I have extracted all the rock tables for all the cells, and then I have classified them. I have defined some clusters of cells. In that case, you can see how I clustered the cell based on the slope of the compaction, which is the y-axis, and the extent of compaction, which is the x-axis. You know, I've defined some clusters of cells, so we're definitely not rocket science. Yeah, this is what you see, what it gives in 3D on this small sector model. You can see that it reflects to some extent the rock properties. So the weak cells, the weak cells are located in the same area, more or less, and also the initial stress regime, because in that case it impacted because we were dealing with a structure which was nearby a salt dome, so which makes that stress regime is very difficult to evaluate, but without with simulation. Okay, we have to bear in mind that, and for these rocks classes and those rock compaction tables, I have performed one flow simulation. So just to give a flavor, feeling of computation time. To perform a fully coupled flow geomechanical simulation, which is a conventional way of doing it, it requires just on this simple model 24 hours. To do just one geomechanical simulation, it lasts something like almost 8 hours. And then I had performed 7 flow simulations, which lasted something like 5 minutes each. So it was really quick. So altogether, the fast flow geomechanical coupling takes 8 hours, and it's applicable to any kind of scenario and any kind of configuration. Whereas just one fully coupled flow geomechanical simulation takes 24 hours. It's just what matters is not to bear in mind, those figures in absolute terms, but rather the difference. Okay, that you get really much faster with the FFGC method, fast flow geomechanical coupling, rather than the conventional one. And here is the results. So here, this is, remember the graph of one of the first slide. This is our case when we take into account compaction, so the continuous line, okay? And when we don't, so we see that we cannot neglect compaction. And here is what happened with the fast flow geomechanical simulation. So the symbols correspond to a different number of rock classes, and we see that basically after so initially the small square represents the case with 10 rock classes, and then the triangle that's 20. The small there is another symbol which represents 70. And what we see is that after 70, with more than 70 rock classes, basically we reach convergence. So with 70 rock classes, we know that we replicate exactly the same results as the fully coupled flow geomechanical simulation. But that just requires a few minutes, whereas that requires hours. So we have reached convergence, and we are sure that we replicate the same results as a conventional flow geomechanical simulation, which is very interesting. I have also applied this methodology to a case where we inject water. So this is a case of a well which would have been initially a producer, and then after a small shut-in, the black is the bottom hole pressure. So initially you see it produce oil and gas, and the bottom hole pressure decrease. Then there is the shut-in, okay, and then we inject water, okay, the bottom hole pressure increase, and this in blue, this is the water rate. In that case, this method works also, but there is a but. I have assumed that
you're almost out of time.
Okay, I have assumed that there were no plasticity in the water injection. So this is one limitation. So to conclude, I have defined one method which enables us to replicate a fully coupled flow geomechanical simulation, but it doesn't require to perform it. This method is called fast flow geomechanical simulation, and it reduces significantly the simulation time. It's applicable to any kind of compacting reservoir, and it's really easy to implement. However, it has not been tested for injection case, so in plastic condition for injection when there is, for instance, hydraulic fracturing. That's it. I would be glad to accept any question if there are.